this was where we left off, doing this visual connection. That we had spent most of the previous part of the class connecting fossil fuel burning to global temperature, and now moving to this branch of the diagram. And I talked about how there were some prerequisites to understanding this. So the goal is to understand the connection here between anthropogenic greenhouse gas emissions, human-caused greenhouse gas emissions, and these extremes. And the four things that we were talking about last time were thinking about how scientists can assign various levels of certainty or confidence to different statements. And so the IPCC has this kind of formal way of doing that, of assigning confidence and likelihood, that when they say something is very likely versus more likely than not, there's actually numerical values of percentages that they assign to that, which I think is useful, and is it's useful for delineating what we're sure about versus what we're less sure about. We talked about the definition of climate change, which we've kind of hadn't formally defined previously, but it becomes important when we're thinking about extreme events, particularly events that are extreme because they're infrequent. And so we talked about the definition of climate change in terms of these perpetual states. So you have to kind of abstract away from just like, are things going up? Are things increasing with time, or are things decreasing with time? You have to kind of abstract to this idea of, what if we were to double CO2 concentrations in the atmosphere from where they were in pre-industrial levels? So from 280 parts per million to 560 parts per million. And then we were just to let that climate state be the way it is for an indefinite amount of time. And you'll see, like, sometimes in global climate models, we'll run a model for like 1,000 years under that new state. And the reason that you have to think about it like that it's for this indefinite amount of time is that you're trying to think about how often do very infrequent events occur. So if you're interested in a 100-year flood or something, then you have to think about, like, how often would that flood that's a 100-year flood that happens once every 100 years in a pre-industrial state, how often would that happen under a state with double CO2 concentrations in the atmosphere? And when you look back in the past, there's never been some time period where the climate has just been indefinitely the same amount of greenhouse gas concentrations for thousands and thousands of years. And so that's why you have to kind of create these hypothetical situations to really isolate isolate what you're actually trying to quantify in terms of the influence of greenhouse gases on those things. And so we can only really do that in model world. And then when we're looking at observations, then we just have to kind of infer how greenhouse gases are changing some of the odds of these various things. And it's just one of the things that makes it complicated to do. We also talked about different ways of quantifying weather and climate extremes. So with global temperature, it's just this very straightforward thing. A temperature is a temperature, you read it on a thermometer. But when we start talking about these other things like tropical cyclones, we find that there's a bunch of different ways to quantify them. So there's frequency, how often something occurs. There's intensity, which is how severe it is. But then even within intensity, you could talk about different things. You can talk about the rain rate of a tropical cyclone. You can talk about the wind speed of a tropical cyclone. And that applies to all of these different events, different ways to measure their intensity. Other things in terms of quantifying them, you can talk about their duration, so their lifespan, how long do they last when they occur. You can talk about their size in terms of spatial extent. So these are just other ways in which this stuff becomes complicated, is that sometimes you'll have one signal going in one direction for one way to quantify a thing, and then going in another direction for another way to quantify a thing. We've actually seen that with fires, in California, where we're seeing frequency decline, as in number of fires per year is decreasing in California. But when they do occur, they're much bigger. And so then the total spatial extent of fires has been increasing. But it's just, it's something that then you could have a headline that says, well, did you know fires have actually been decreasing in California? Well, that's the number of fires, so you can kind of lie with true facts because it gives a misleading impression about what's actually going on. So just another thing to keep in mind there. And then tools for understanding was where we left off. And so I wanted to pick up there. And the main tool that we use to understand kind of everything in climate science is really climate models. It's really become the predominant mode of understanding causality within the climate system. So this arrow of causes to extreme weather and climate events. So I have a couple of videos here I want to show about climate modeling that just introduce it. You hear that?
Earth's climate has been through a lot over the past few billion years, and at this point scientists have a pretty good handle on how our planet has changed over time. But we talk about the future of the climate too, about how it's changing more quickly than it has in the past, and about the dangers of rising temperatures and more severe droughts and storms. Our methods for predicting the future of climate are a little different than those for reconstructing the past. The past leaves physical records we can study in things like tree rings and ice cores. The future requires us to be a little more abstract. So we mostly predict the future of Earth's climate using computer models, mathematical reconstructions of our atmosphere that account for as much detail as possible to produce an accurate simulation. And it's taken decades to build them up to the point where we can be confident that what they say is accurate. But it is. And what the models say is that our climate is changing, and humans are making it happen. Global climate models, or GCMs, grew out of early computerized attempts to model the planet's atmosphere in the 40s and 50s. Scientists weren't even trying to predict the future, they just wanted to create a representation of the Earth's atmospheric system as it was at the time. That was hard enough. Climate models, then and now, divide the Earth's surface into chunks a few hundred kilometers on a side, each with different properties like air movement and surface temperature. Then the computer calculates how all those chunks interact with each other to see how things change over time. Those early models were super simple. They did things like combine land and sea into a single damp surface with no geography, or represent the Earth as a cylinder instead of a sphere because the poles confused the computer. Thankfully, this didn't lead to a whole movement of cylinder Earthers, though. All this simplifying was necessary because early supercomputers were kind of limited. We're talking like 5 kilobytes of RAM. Your phone has like 500,000 times that much. Still, it was enough to come up with a crude picture of Earth's atmospheric currents and its wet and dry regions. Eventually, though, scientists wanted more than just a model of the atmosphere around a featureless cylinder. They wanted something that fit an actual planet. Now, they could make the model more accurate by making the chunks smaller, but that would take more computing power. And what about the effects of mountains on air movement? What about the warm and cold water circulating in the oceans? To answer those questions, climate modelers needed more juice. By the 1970s, they were also beginning to worry about the greenhouse effect of the carbon dioxide we were adding to the atmosphere using fossil fuels. They thought it could trap the sun's heat and cause the planet to warm. At the same time, computers were getting powerful enough that they weren't limited to modeling the present anymore. So programmers wanted to start using models to predict future changes in the climate. But before a climate model can be turned loose to predict the future, it has to be able to predict the past, what's known as hindcasting. And that's an important test, because if the model's predictions match what we know already happened, we can be more confident about what it says will happen in the future. Temperature records go back a century or more. If you start a model in 1850, it should be able to progress through time and match the general trends in temperature we already know happened. And by the late 1970s, climate models started to be able to do this. In 1979, a report pulling from 2 different climate models suggested that the Earth's temperature would increase as atmospheric carbon dioxide increased. Specifically, assuming twice as much CO2 in the atmosphere, they predicted an increase between 1.5 and 4.5 degrees Celsius, which trends suggested could happen before the 21st century was up. That range has proven pretty reliable ever since, and it still fits the warming we expect to happen over the next century or so, even as models have become much more powerful. So models in the 70s were able to answer one simple what-if question. What happens if the amount of carbon dioxide in the atmosphere doubles? But these days, you can carry more computing power in your pocket than those early programmers ever dreamed of, and using use it to send people pictures of your cat that disappear after 10 seconds. Truly, it's a golden age. And not only are cat pictures better, but so are climate models. We now have the resources to ask and answer more detailed questions, and boy do we have a lot of them. Governments want to know what will happen in detail in their corner of the world, and scientists want to know what will happen if we take measures to stop global climate change as opposed to letting emissions run rampant. With the models we have now, we can produce more customized predictions based on different scenarios of what humans might do in the future, like how much carbon dioxide will be emitted over a given amount of time and how much land will be used for agriculture. You can also use these models to basically run the predictions backwards and calculate the factors that would lead to a certain amount of warming. So for example, if policymakers want to see what changes should be made to limit overall global warming to 2 degrees Celsius, they just have to use a climate model with the appropriate parameters. That said, just because it's the 21st century and computers are awesome now, doesn't mean that climate models have reached their perfect final form. The Earth's atmosphere is an unbelievably complex system, and we don't yet have models powerful enough to track absolutely everything. We also can't account for every single thing humans do now or might do in the future. So we now know a lot about what will happen, but there's still work left to do in perfecting our predictions. For example, up until 2012 or so, models weren't that great at predicting sea level rise. They undershot it pretty badly. UN reports in 2001 and 2007 made predictions for sea level rise that failed to track with what we observed via satellites by about 60%. That might be because the models didn't fully account for the rapid changes in the ice sheets over Antarctica and Greenland. For the UN's most recent report in 2013, the models were reprogrammed and the projections for sea level rise increased to be more in line with what we're seeing happen. We want our models to do better, in part because we want to know what's going to happen to our climate, and in part because accounting for all the variables is just good science. With these constant improvements, every new prediction can be more detailed. And in the last couple of decades, we've started to be able to tailor predictions for specific regions, which is helpful because people and governments in different parts of the world want to know very different things. A farmer in Southern Europe might want to know if drought will affect their crops more severely in the future, while an islander from the Maldives might be more concerned about their country being completely swallowed by rising seas. Now we can try to answer those questions, and a lot of the answers aren't encouraging. No matter how you look at it, the models are very clear that the planet is warming. That's one of the easiest things to predict. I mean, we've been doing it since 1979. If we pump more heat-trapping greenhouse gases like carbon dioxide into the atmosphere, the numbers come out warmer. There are factors other than greenhouse gases that the models take into account too, like particulate matter from volcanoes and coal-burning power plants, which can have a cooling effect. And we know the oceans will slow warming for a while by absorbing CO2 until they run out of capacity. But all the predictions say the warming caused by greenhouse gases will have a stronger effect. Even in scenarios where governments around the world work quickly to limit and phase out greenhouse gas emissions, climate models predict that the Earth's temperature increase will be at least around 2 degrees. But in other scenarios where we take less aggressive action or no action at all, the planet's average surface temperature goes up by more like 6 degrees Celsius, which if you're used to Fahrenheit, that's 11 degrees. That's hot. But higher temperatures are far from the only consequence of climate change. Using models, along with other tools, researchers predict all kinds of other effects. A comprehensive report by the US Global Change Research Program, published in 2014, lists some of the consequences. It emphasizes effects on North America, but similar things would happen all over the world. With more and more time passing between periods of freezing temperatures, plants could experience a longer growing season. Now, that could actually have a net positive effect of causing plants to take up more CO2, so less stays in the atmosphere. But the good news pretty much ends there. In general, around the world and in North America, there would be changes in the distribution of precipitation, including rain and snow. And the changes tend toward increasing extremes. A warmer atmosphere holds more moisture, so wet regions will get wetter. But models show shifts in large-scale movements of air that would exacerbate dryness too. So for example, the dry American Southwest will get even drier. And major events like droughts, heat waves, and powerful storms will get worse and more frequent. The effects of climate change on Atlantic hurricanes are hard to predict. We don't know for sure whether it was responsible for the devastating 2017 hurricane season. But we know that as the global temperature increases, the temperature of the surface of the ocean does too, and warm ocean water is hurricane fuel. Historically, warmer years don't produce more hurricane landfalls, so we may only see stronger storms, not more of them. But that's not a sure thing. Climate change will have other kinds of effects too, like rising sea levels, melting ice caps, and changes in ocean currents. But it would take a whole other episode to talk about them all. which is exactly what we did a few years ago. Thanks to decades of work improving climate models, we now have a very good idea of what's happening, both globally and regionally. And even though our models have gotten much more detailed over the years, those predictions of increasing temperatures have stayed constant, which is a good sign for the science of climate modeling, but also maybe a cause to be a little worried. We've always known that the Earth wasn't just a damp cylinder, but as our ability to model the climate has improved over time, we've learned a lot about how our planet works and what we're doing to it. Thanks for watching this episode of SciShow. If you're interested in learning more about the effects of climate change, we have another video about just that topic.
I'm just going to show one more academic video, just 2 minutes.
We know how and why weather occurs. It varies over minutes, hours, and days. Climate is the average weather. We understand the physics and chemistry that describe the interactions between the atmosphere, the oceans, the land surface, and the biosphere that create weather and climate. Scientists use this knowledge to program computer models that simulate our weather and climate. These are called global climate models, and they provide forecasts of weather over the next 1 to 7 days, and assessments of causes of past climate variability and projections of future climate change. There are over 40 global climate models internationally, one of which is Australia's ACCESS model. ACCESS provides weather forecasts for Australia. Looking a week ahead, the model enables meteorologists to forecast rainfall and temperatures. Looking decades ahead, the model enables climate scientists to estimate ranges of temperature and rainfall. The model works by dividing the Earth into boxes. Typically, the boxes measure about 200 kilometres by 200 kilometres. To project future climate, we start with the measured or estimated conditions at every corner. The model steps forward in time, creating new conditions at each corner. The output from each step becomes the input for the next, allowing us to run the model as far into the future as required. Over regions with complex mountains or coastlines, better climate simulations require dynamic downscaling. Downscaling models have boxes that typically measure 50 kilometres by 50 kilometres or less. Models can reliably simulate the climate that we have experienced in past decades and future decades based on different assumptions about how greenhouse gases will increase. Climate models help us understand past climate variability, manage weather fluctuations over the coming days, and plan for long-term climate change.
Okay, so that should be a pretty good kind of introduction to climate modeling. I think there's two things that are worth pointing out in more detail about climate models. One is kind of a strength and one is a weakness. So starting with the weakness first, it was mentioned a couple times how these climate models work as they break up the entire Earth system into grids. And this is a visual depiction of how that resolution, that grid box resolution, has changed over time. So starting with, this was the first assessment report of the IPCC. So this is 1990. This is what the climate models look like in terms of representing Europe. And then this is by 2007. They looked more like this. And now they would maybe be, another half of the resolution. So it'd be, you'd see 4 times more grid boxes now, but it's still relatively coarse. If you're talking about, drilling down to some location where you see, here Italy is just a handful of grid boxes, and so now it might be 13 grid boxes or something like that. Still not a ton if you want to actually get down to the level of, something that's as important as extreme precipitation events in one part of the country versus a different part of the country. So that's a weakness. And when we're talking about, we're trying to get to the idea of using models to assess tropical cyclones, we can see that in all of these resolutions, climate models are not fine enough spatial scale to resolve things like hurricanes. So the model itself is not actually producing hurricanes, or at least it hasn't been historically. So the models that have been used over this time period, when climate science has matured, the models don't actually produce hurricanes. So you can't actually look in a model and say, oh, the hurricanes have gone up as CO2 has gone up. You kind of have to infer that as a secondary step. You'd say, well, the sea surface temperatures have gone up, and then we have other reason to believe that sea surface temperatures affect hurricanes, and so that's going to have some implication on hurricanes. But that's this additional step, additional chain in your reasoning that makes it more difficult to directly attribute some change in an extreme to change in greenhouse gas concentrations. So that's definitely true historically, but I'll show you some simulations more recently where they actually do produce hurricanes. But that gets me to the topic of the strength of climate models. And you kind of hear this embedded in the language that they talk about, that they're using the language of prediction, and that the models are telling you something that you didn't know before, that you run a model and it gives you some output, and you could be surprised by it, or it could confirm a hypothesis, or it could reject a hypothesis. And I just want you to think about like whether or not that makes sense to you, because a model is just computer code that someone coded up, someone put together in a computer. And so how can it be the case that it's making predictions? Like, isn't it just gonna tell you what you told it to tell you? Like, why can't you just go talk to the computer engineer and say, well, what did you put in the model? And then why don't you just tell me that? Why do we have to go through this charade of running the model and then seeing what the output is? Yeah, so it's definitely this idea of interactions between various components of the system that you don't actually know what the emergent large-scale result will be. All you know is like the small-scale relationships between things, and you put that into the model, and then it will calculate what the large-scale result is. So I think the easiest way to think about this is comparing it to a statistical model. So these global climate models are physical models, as in not physical model like I hold a physical toy car or something, but a physical model as in it uses the equations of physics as its like bedrock underlying equations. So they're based on physical laws. And so then phenomena like tropical cyclones are not programmed directly into the model. They emerge from the underlying physics. So you put into the model just like these are kind of the three most fundamental equations in climate science. This is conservation of mass, conservation of momentum, and conservation of energy. And so all those are stating is that if mass moves out of one grid box, it has to move into the adjacent grid box. And if momentum moves out of one grid box, it has to go into somewhere else. So you're keeping track of all of that at all times. But the point is that these are physical laws. They're not statistical relationships. So then you can, with a high enough resolution climate model, you can do this experiment that we were talking about. So if we have very advanced computing with high resolution, we can compare the climate, the tropical cyclone climate of the North Atlantic, for example, under 1,000 years, where we're holding CO2 levels constant at 280 parts per million. We can compare that to another 1,000-year run where we're holding CO2 levels constant at 560 parts per million. And so then you can like start to see, okay, what is the climate change in those tropical cyclones? Do we get more of a certain kind? Do they shift their distribution? And we can even get at rare events because we're running the model for such a long period of time. But this type of experiment is very different than what most people are used to when they're thinking about mathematical models, which are statistically based. So if you think about like kind of the simplest statistical relationship that you learn in math class is just the straight line, y equals ax plus b. And so an example of this applied to tropical cyclones might be something like number of hurricanes would be y. Number of hurricanes equals a times ocean temperatures plus B. So what I've done here is I've kind of imposed a relationship on this. I've defined that the number of hurricanes is related to ocean temperatures. I've just defined that ahead of time here. And then I've said, okay, there's a number A that that tells us what the proportional change of ocean temperatures, or what the proportional change of hurricanes is to ocean temperatures. And so then as a modeler, I could say, okay, this value is 5 or whatever. And so that is not very convincing. If models were built like this, then it would be the case that it would just kind of be like, oh, we'll just go ask the modeler what they put in and then argue with the modeler why they made this relationship like this and why they chose a certain value for A. And we don't even need the modeling relationship. But this is not how climate models work. They're not statistical relationships. There's not some imposition by the human on the code that tells it to do anything in particular with, for example, tropical cyclones. So I'll show you some output from a model that's actually simulating. So this is a climate model. This is one of these new advanced climate models with super fine resolution that is simulating clouds and tropical cyclones over the 2005 hurricane season. So what that means is that you tell the model kind of what the sea surface temperatures were during that time period, but then what it's doing here is it's creating storms, it's creating tropical cyclones, but there's no line of code in the model that says, make a tropical cyclone start here and make it rotate counterclockwise and then make it go over here. All of that just emerges from the underlying physics. So when you take a climate model and you double CO2 concentrations in it, and then it starts doing something to tropical cyclones, you can think of that as the model predicting something or it giving you additional information. It's not just that the coder, the modeler told it to do something ahead of time. It's an emergent property of the system that it's somehow, it's calculating that should happen based on physics, not that it was just telling us what we told it to tell us in the first place. So this one, we'll go through the whole season of 2005. And again, these tropical cyclones, no code that says for them to come up and exist. They just emerge from the underlying physics. And so that gives us a good, bit of understanding or good confidence that we actually understand tropical cyclones and that they emerge from the physics that we understand. Does that make sense why it's stronger to have a prediction by a physical model than a statistical model? Because a statistical model, you're kind of just telling it ahead of time what the answer should be. Yeah, so that means that climate models are really versatile. So you can use them to make predictions about climate under radically different conditions than today. So you could take a climate model and take out the continent of India and say, how does that change the precipitation in China, right? You can't do that with a statistical model because you would need some historical, data on what that has done in the past or something like that. But you can do it with a physical model. Another example is, this is a paper that came out last year called The Climate of a Retrograde Rotating Earth. And so they asked the question, what if the Earth was rotating in the opposite direction? How would the global climate change in that case? So again, there's no historical relationship you can base this off of. You can only do this with a model that's based on physics. And you might think this is a trivial thing, but it really does help us kind of understand climate better, not necessarily climate change, but just the global climate. So, one result from this is the US Southwest or the US Southeast would be like a desert, where today it's very much a warm, humid area. but the US Southwest is a desert, and largely that has to do with the pattern of weather and how it goes from west to east, and that has to do with how the Earth is rotating. And so if you spin the Earth in the other direction, you get a different climate. But the point here is that we can use these climate models to actually give us new information about how things like tropical cyclones should change. Okay, one more thing about thinking about these extremes and their connection to increasing greenhouse gas concentrations is this idea that weather and climate predictions can be difficult to validate or to compare to observations when it comes to these extremes, because the influence from increasing greenhouse gases, increasing greenhouse gas concentrations can be relatively small compared to other influences. And this is not the case when we're talking about certain things like global temperature, but it is the case when we're talking about some things like tropical cyclones. And so the way that that usually is formally talked about is it's said that the phenomena has a low signal to noise ratio. So signal to noise ratio is an expression you'll hear a lot, especially in statistical contexts. I think Nate Silver's book on statistical prediction is called The Signal and the Noise. So it's something that comes up in many different areas, but in the context of climate change, and in particular in the context of extreme weather and climate events, the signal and the noise are defined like this, where the signal is the influence on something, on X, from anthropogenic greenhouse gas emissions. And then the noise is the influence on that thing from everything else. So it could be kind of just natural, random weather variability, or it could also be, other human influences. So like with fires, for example, we talked about the signal, the influence of increasing greenhouse gas concentrations on fires through drying of the land surface. But then noise, in that case, might be the influence from changing managerial practices in forests. So things with like high signal to noise ratio are what we've been talking about so far in this class, like atmospheric concentrations of greenhouse gases. So this is our graph of our three main greenhouse gases that are driving current climate change: carbon dioxide, methane, nitrous oxide, from the year zero to the Industrial Revolution. Some variability. So that's our noise, right? That kind of goes up and down. There's some random ups and downs for whatever reason. And I'm sure that there's some people that study exactly why it went down here and why it went back up. But once humans started putting greenhouse gases into the atmosphere, it just totally overwhelmed all that noise, right? So it's very, very high signal to noise ratio. The signal is very, very large compared to the noise. And so all of that noise is just swamped out, and the signal emerges just very, very directly. So that's very high signal to noise. High signal to noise example would be global average temperature. So this is land average temperature. This is actually smoothed with a 10-year filter. And so when you look like year to year, there's some noise due to El Niños and other factors, but it's still a high signal to noise ratio where increasing greenhouse gases in the atmosphere has this very large effect on global average temperature relative to the natural kind of random ups and downs. And it's such that, we get like a new record of global average temperature every 4 or 5 years. So it'll go up, and then you'll have, some randomness that causes it not to be a new record the very next year. But within 4 or 5 years, we're setting a new record pretty consistently. And so that tends to be actually different than a lot of these, the relationship to local changes in weather and climate extremes. These tend to have a much lower signal to noise ratio. And so here's just a visual kind of example of that, is that you might have a situation, and this doesn't have to be tropical cyclones, it could be any type of kind of extreme event that you're interested in. So this is a hypothetical situation from 1900 to 2150. And then the number is just arbitrary because I just made up this data. So some weather climate phenomena. And let's say we hypothetically have, this is our historical observation of that thing. So it looks like there's maybe an upward trend, but it's not super obvious. And let's say that this is our noise level, that this is our kind of range, our envelope of natural variability of this thing. So it could potentially go up or it could potentially go down in a stable climate. But what climate models help us do is they help us kind of understand, even within a low signal to noise ratio situation, what the influence of climate change might be on that thing. So we can point out that, like, okay, the most recent observation of this thing is not outside the natural range of variability. It's not like we're setting a record every single year like we are with global temperature. But we can use a climate model to kind of to infer, based on physics, again, based on our physical equations, what the signal, what that influence from increasing greenhouse gas concentrations might be. So this line here, this red line here, might be telling us what that actual influence from global warming is. And so then we would expect, in this made-up data scenario, that by the end of the century, you kind of have this emergence where you're in this totally new situation where you're seeing even your lowest values are going to be higher than your highest values would be under a no climate change scenario. And so we end up with data oftentimes like this with these weather and climate extremes, is that we're kind of expecting them to emerge later in the century if greenhouse gases continue to rise on some projected scenario. But it's not the case that, like, what we've seen historically is like super dramatic. It's not like the change in greenhouse gas concentrations in the atmosphere where the signal is just so overwhelming compared to the noise that you can just see hockey sticks. It's much more subtle, like something like this, where we would expect maybe 100 years into the future, then you see this like kind of hockey stick emerge. Okay, so that was kind of my last preliminary. And so let's think about, all these things in terms of moving to tropical cyclones. So I mentioned a little bit background of tropical cyclones last time. Obviously these, devastating storms that originate in the tropics, and we call things that rotate around low pressure systems cyclones in meteorology. So that's why they get the name tropical cyclones. I mentioned last time where they occur. So we have the ones that we're most familiar with are these ones that occur in the Western Atlantic. And they also have on this diagram the kind of seasons that they occur most frequently in. So August through October here. There's a local maximum of occurrence in the Eastern Pacific here, which don't get a lot of attention unless they hit Hawaii, basically. So they don't get a ton of attention because they don't make landfall. And then we have other basins, so the North Indian Ocean over here and the Western Pacific are a local maximum, and then in the Southern Indian Ocean and the Southwest Pacific. And so this gives you some idea of just the activity in these regions. So this is, let's see, average number, so frequency here, average number of tropical storms. So tropical storms are anything above 39 miles per hour, where over here we have hurricane, so it has to be above 73 miles per hour. And so we can see the basin that has the most is this northwest Pacific region. So this region right here is what typically has the most tropical cyclones every year. So 16 or 17 hurricanes a year, and 26 of these storms above 39 miles per hour. And then the ones that we hear the most about in the Atlantic, we on average have 6 hurricanes per year and 12 tropical cyclones per year. And so this year we more than doubled both of those. So we're at 30 tropical storms this year, as opposed to our average being 12, and I think 13 hurricanes this year. So that sounds very dramatic, and I'll show you what that looks like on an actual graph comparing the frequency through time. The other thing that gets mentioned is the category, the severity, so intensity of tropical cyclones. And this is kind of just a visual depiction of that this is a category 1. You're kind of bowing your palm tree. Category 2, they're still not showing water, but more wind. And then category 3, 4, 5, where 5 is completely devastating. And then you can see the storm surge level if you're on the coast of category 5 hurricanes. It's, I think down here we have storm surge. Category 5 is greater than 20 feet. So the storm itself is bringing in ocean water that in the vertical is 20 feet. So obviously, totally devastating to infrastructure right on the coast. And it's kind of amazing that these structures can survive this, because it's like, why would you build this at 20 feet above sea level unless you think it could survive the winds? But apparently plenty of them do. But yeah, you'll see these structures on stilts along the Gulf Coast and East Coast of the United States. So I only bring that up because you'll see in some of these conclusions about historical and projections about future tropical cyclones, they'll make a distinction between major hurricanes and just regular hurricanes. And so a major hurricane is anything that's 3, 4, or 5, category 3, 4, or 5, or they'll sometimes just talk explicitly about changes in category 4 and 5 tropical cyclones. So those are the most severe. Here is just kind of a trivial thing showing historically from 1950 to 2017 where tropical cyclones have hit on the US East Coast and Gulf Coast. So then this is by category. So like Hurricane Andrew in 1992 is very famous because it was a category 5 hurricane that hit right on a population center. So right on Miami. So that was a hugely devastating hurricane. We can see, we all know Hurricane Katrina hit Florida in 2005, right? So maybe you didn't know, but it did hit Florida first. It formed out here, hit Florida, went into the Gulf Coast, and then it should be over here as well. Yeah, Hurricane Katrina here. So it hit New Orleans later as a category 3. It first hit Florida as a category 2. Yeah, so some other ones, Ike is a big one. Anything around, obviously, population centers can cause more and more damage. And that's another big thing is you'll see, I don't have slides on that today, but you will see like big spikes in the damage caused by hurricanes. And a lot of that is due to just there being more infrastructure in harm's way, that we're building a lot more on the coast over time. You can imagine what Miami looked like in 1950 versus today. There's a lot more to damage. And so you can get a lot higher damage totals when the same hurricane hits today versus in the past. This is one more preliminary thing. This is showing the return period. So the average time that you would have to wait before you see a hurricane. So this is just see any hurricane. So 6 in Miami means that on average, you would get a hurricane every 6 years. That's looking at the historical record. And so we can see like kind of the points of land that jut out, like the tip of Florida and then North Carolina. They tend to have shorter return periods that you see hurricanes more frequently. But this, this gets at, again, like why you need really long, you need to conceptualize climate change in terms of long time scales, and you literally need long climate model runs if you wanted to see like, how is the return period changing for hurricanes that hit New York? If in the base state we expect on average every 20 years, you can't just run a climate model for 20 years from 2000 to 2020 and then say, oh, how often did New York get a hurricane? Well, it didn't get a hurricane in that time period. Does that mean anything? No, it doesn't mean anything, because you need to run it for like thousands of years and see kind of the frequency changes of that thing. Okay, so going back, that was just tropical cyclones background. Going back to our connection between increasing greenhouse gases and tropical cyclones. Our kind of base fundamental thing that we should think about is that it is the case that tropical cyclones like warm ocean temperatures. So there's kind of like a threshold around 27 degrees Celsius, which is around 86 degrees Fahrenheit, that you see a large increase in tropical cyclone formation. And so if more of your ocean is above that temperature, then you would expect to see more hurricanes. And so this is why we see a seasonal cycle in tropical cyclones, why they peak when ocean temperatures are warmest during the year. So this is the kind of average frequency of tropical cyclones and hurricanes in the North Atlantic basin over the calendar days of the year. And so it peaks around September 10th. The season peaks around September 10th because every single year, that's when our sea surface temperatures are the warmest, or that's the main reason anyway. The other thing though is that if you just thought about that, then we would expect tropical cyclones, their frequency to be increasing with global warming, because we know that increasing greenhouse gases increases sea surface temperatures. The other main ingredient though is that they also like a kind of tranquil atmosphere to develop into. So of course the atmosphere right within the tropical cyclone is very violent and very high winds, but they like to form in an atmosphere that's relatively tranquil and relatively just kind of clear. And it turns out that so the technical term is low wind shear, but it turns out that these things might be in conflict as we put more greenhouse gases into the atmosphere. So greenhouse gases increase sea surface temperatures, but in the region where a lot of hurricanes occur, we expect actually wind shear to kind of increase. And so then that makes it harder for these storms to develop. So they might have countervailing factors influencing tropical cyclones, one kind of pulling you in the direction of more and more intense, and one pulling you in the opposite direction of having less tropical cyclones, and kind of for them to possibly be, disintegrated easier when they do occur. So that's what makes it complicated, and why you'd want to run a model in the first place to see, okay, what wins out. And you can ask a model that question, because no one programmed the model ahead of time to tell you which one wins out. What the model will do is it will calculate, it will try to figure out with all of the underlying physics, how the sea surface temperatures will change, how the atmosphere will change that the hurricanes are growing into, and then it will give you an answer, which you can't necessarily take as the truth, but it's at least a piece of evidence as to whether or not we think sea surface temperatures will win the battle, or a tranquil atmosphere will win the battle. And this is, still an active area of science. And I'll show you one kind of reason for that, is that if you look at historical trends of tropical cyclones in terms of frequency, so number, it's basically flat. So this is 1990 to 2019, so not updated yet for 2020. So 2020, I'm not sure if globally it'll be that huge of a signal, but in the North Atlantic, it's a big record year. But globally, this is showing, okay, named storms, cyclones, major cyclones. So named storms, that's anything above 39 miles per hour. Cyclones basically is any hurricane, and then major are these category 3, 4, and 5 hurricanes. And so this is just going year by year and counting the number that have occurred. And there's not any major dramatic trend globally in these things. Here's another, remember, different ways of measuring these things. This is a common measure of intensity of tropical cyclones called ACE, which is, it's called accumulated cyclone energy. And it's just this index that kind of adds up all of the wind speed throughout the entire lifetime of a hurricane. So it's kind of taking into account how long it lasts as well as whether or not it occurred. And so that's flat too globally. So both of these things are showing no real dramatic trends in terms of, tropical cyclones occurring, period, so frequency, as well as their wind speed. And I'll show you that when we look at rainfall rate, it might be a little bit different. But I do want to just pause here for a second and say that this is good news. I think a lot of people, like, when I show something like this, they're thinking like, wait a second, like, what side are you on? You're kind of like taking the wind out of my sails in terms of, being an advocate for climate action or something like that. And I just want to say, like, there's plenty to worry about climate change, that you don't need to, overstate the case when it's unnecessary. And so I think this is really good news that so far there has not been some crazy dramatic increase in tropical cyclone frequency or average wind speed. Again, because we're so far away from solving the problem, that if it was the case that we've doubled the global frequency of tropical cyclones already, and we are on track to quadruple it and multiply it by 8 or something like that, that would be much worse news. So I do want to say that this, I think, is good, and you should embrace that this is the case and not be somehow disappointed or something. So we can also look basin by basin at these trends. So this was globally, and then this is the same type of graph for the Northwest Pacific. And so same thing, named storms, hurricanes, major hurricanes. So we have kind of this is going back to 1970. We have, kind of some decade to decade ups and downs, but again, no huge trend here, no hockey stick. Here's our basin that we care the most about, and I put on here, I had to update this myself, I just drew on here what the latest totals are for 2020. And so this is our record year in terms of named storms in 2020. Hurricanes, not quite at a record for hurricanes, but a record for named storms. And then major hurricanes, not quite at a record either. And so this is a basin that we do see definitely, from the 1990s, an increase in frequency in the total number of storms. And so that's a piece of evidence that's showing perhaps as it gets warmer, we should expect to see more tropical cyclones, but that's actually not what the models say. So they say that we should see less, but more very strong storms. So this is where at what point do you think the observations are just kind of randomly going in one direction, but they'll eventually go in another direction? And at what point do you think the models are wrong? This is why this is a very active area of the science. So this is kind of the one basin where we do see a trend towards more tropical cyclones. but it's, again, it's not quite, it's not as dramatic as what you look at when you're seeing changes in the concentration of greenhouse gases or in changes in like global average temperature, for example. So going through the other basins, this is the North Indian Ocean. So frequency kind of flat, but we do see perhaps a trend in the accumulated cyclone index, that index that takes into account wind speed over the entire lifespan of the tropical cyclones. This is the South Indian Ocean. Again, kind of flat in both of these metrics. And then the South Pacific, flat, or if anything, kind of looks like a decrease in tropical cyclone activity in that basin. So I will summarize that by saying that we definitely don't see any strong trends towards there being more tropical cyclones globally. And if you look at you go back through and look at major cyclones, so that would be the lowest level on all of these, not really globally do you see some dramatic trend in major cyclones either. So the strongest ones. But what can we say about tropical cyclones? Well, this is kind of a summary by basin of, this is not historical, but it's projections of the future, predictions of the future, kind of what the models say should be happening. And I think this kind of summarizes like the state of climate science when it comes to tropical cyclones. So they have 4 different metrics here, 4 different ways of quantifying changes in tropical cyclones. And so that's what each one of these graphs in each basin shows. So we have 1, 2, 3, 4, and that corresponds over here. So 1, 2, 3, 4. So these are our 4 metrics in each basin. And so the first one is all tropical cyclone frequency. How often do we see tropical cyclones? The number. And the values in each one of these graphs is the percent change basically in the future climate compared to the past climate. So they use the year, this is from models, the year 2081 to 2100 compared to early in the century. So the year 2000 to 2019. And so any one of these lines above, so there's the 0 line in each one of these. So any line above means an increase, and then there's an uncertainty range. And any line below means a decrease. So if we just look at our North Atlantic basin, we can see, what does it say for all tropical cyclone frequency? Well, big range, so from over 50% increase to over 50% decrease. But then the central estimate is a decrease, that what we're projecting is less tropical cyclones in the future. That's not what we're seeing. We're seeing in this basin, this is the one basin that we're actually seeing an increase in frequency. So that's why there will be many more papers on this. In terms of the category 4 and 5 tropical cyclone frequency, those most severe, the range again is huge. It goes from off the charts 200% increase to off the charts 100% decrease. And then their median here is basically a 50% increase. So this is, again, these are predictions, not historical observations, but it's projected that we would have a 50% increase in category 4 or 5 tropical cyclones, which would be very bad because those, very disproportionate amount of damage is from these extremely intense tropical cyclones. And so if that's the case, that would be quite bad. Lifetime maximum intensity, I'll just skip that for now. Let's go to precipitation rate. So this is interesting because we see in every single one of these basins, the precipitation rate has a relatively kind of small confidence interval that shading around it is small, and it doesn't overlap with 0 in any of these. So that means that it's a very robust projection, that basically in all of the basins, we think precipitation rate should increase as the ocean temperature increases and as the Earth gets warmer. And here's the global summary of that we see with this precipitation rate, that should increase by something like, I don't know, it's hard to tell, maybe 20% or something by the end of the century. So that's like probably the most solid thing that we can say about tropical cyclones. It's kind of a jumbled thing when you're talking about the frequency or the intensity in terms of wind speed or the frequency of the most intense tropical cyclones. But there's very, very good evidence to suggest that precipitation rate should increase. And I didn't show historical evidence. This is more coming from the models, but there's good just physical reasons to believe the precipitation rate should increase as it gets warmer. And it's essentially just because the atmosphere can hold more moisture when it's warmer. So this is, I'll just do another kind of pull quote from the IPCC report. This is one that I didn't mention last time, but this kind of summarizes the state of knowledge. Tropical cyclone projections for the late 21st century are summarized as follows. There's medium confidence that the proportion of tropical cyclones that reach category 4 or 5 levels will increase. So they're still saying that that's a projection. The average intensity of tropical cyclones will increase by 1 to 10% for 2 degrees warming. So this intensity, they're talking about wind speeds. So kind of a small change in wind speeds. And that the average tropical cyclone precipitation rates for a given storm will increase by at least 7% per degree Celsius of sea surface temperature warming. So that's a pretty big signal there. That precipitation rate, 7% per degree of local sea surface temperature warming. And so we kind of talked about last time the cascading impacts paragraph that kind of combine the negative impacts from tropical cyclones with sea level rise. And so I think that theme is like the most robust thing that we can say about tropical cyclones. And so I just put it here as the safest statement regarding the influence of increasing greenhouse gas concentrations on tropical cyclones would be something like this. Increasing sea levels, which we know are due to increasing greenhouse gas concentrations and due to the expansion of water and the melting of ice sheets. Increasing sea levels combined with the increasing rain rate or precipitation rates from tropical cyclones will make flooding from tropical cyclones worse when they do occur. So I think this type of statement is the safest thing that you can say, and that you're in, it's just a lot more complicated. You're in kind of murkier water when you're talking about wind speeds, or you're talking about category 4 and 5s, or you're talking about the frequency of tropical cyclones. So sorry that this is it's a little bit all over the place, but I'm trying to get that across as well, because that kind of just is the case in terms of what the influence of greenhouse gases is on these phenomena, that it's complicated. So